Authored by veteran chemistry teacher Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up and don't forget to subscribe. We will see you in the next video and thank you for watching.
Today, we'll be introducing the mole concept, and our lesson begins on page 119 and it ends on page 126 from the text Chemistry 11 in Focus. We'll be reviewing atomic number and mass number. We'll also review isotopes and their relative abundance. We'll be talking about Avogadro's number and molar masses for elements, and then we'll provide a summary table for the molar masses of some elements. It will be inconceivable for someone doing masonry to order a quantity of sand in terms of number of grains. Sand is commonly supplied in convenient quantities such as 20 kilogram sacks, tons, or truckloads. In chemistry, a similar thing happens. A quantity is sought that avoids measuring masses of chemicals in terms of number of atoms, ions, or molecules. This quantity is the mole. A mole of a substance contains this huge number here, 6.022 times 10 to the 23rd power of atoms, molecules, or ions, as the case may be. This number is called Avogadro's number, and it is named after the Italian scientist Amedeo Avogadro. The mass of any one of these entities, atoms, ions, or molecules, is incredibly small, and only a phenomenally large cluster of these will have a mass that is easily measurable and convenient to work with. The element carbon, for example, has an average atomic mass of 12.01 U, or atomic mass unit, of course. Expressing this mass as grams give the following. See, you take 12.01 grams of carbon and you divide it by Avogadro's number, and that will be the mass of one carbon atom, or this here. And this is incredibly small. As can be seen, this is very small. However, listen to this. 1 mole of carbon translates into 12.01 grams. So if you take 1 atom of carbon, this is what it weighs. If you want to know, translate that to mass, you take 12.01 grams and divide it by Avogadro's number. This is a huge number you're dividing it by. And that mass for 1 atom of carbon is exceedingly small. But if you use 1 mole of carbon now, that translates into 12.01 grams. See, so we can work with that. As in the case of carbon, quantities in moles of all other elements and compounds translate into masses that are convenient to measure and use. So here's a little balance here. I show you here if you have 1 mole of carbon, a random sample of carbon in the environment, and you weigh that, it will weigh 12.01 grams per mole. I have created a unique method of teaching the mole concept for most of my teaching career that I found to be very successful. Before we proceed with that, it is useful for us to review a few concepts to facilitate our understanding of the mole concept. First, we review standard atomic notation with the objective of arriving at the atomic mass of an isotope of an element. This is a table we're showing you the difference between protons and electrons and neutrons, where they're found. You can see that the mass of one proton is the same as one neutron. And of course, the mass of the electron is very, very small. So we assume, for the purpose of this lesson that we are doing here, that it has a mass of 0. Okay? So here it's telling you the same thing again. I'm just explaining what is happening there. Here we are having 3 different atoms. We are having one of the isotopes of hydrogen, one of the isotopes of carbon, and here one of the isotopes of nitrogen. And you can see this is the mass number here, and that translates into atomic mass here. So you have 1 AMU for hydrogen, carbon will be 12 AMU, and nitrogen 14 AMU. Mind you, we're using one of the isotopes of these. In this case, we're using carbon 12, nitrogen 14, and hydrogen. These are different isotopes. You have carbon 12, carbon 13, carbon 14, and stuff like that. The other ones too. So that's showing you how you change mass number to atomic mass. There's some questions here based on that, what you see here. Now we will revisit this concept of isotopes. Recall from video 3 that carbon has 3 isotopes: carbon 12, carbon 13, and carbon 14. Again, we use the mass number here to find the atomic mass here. So this is the atomic mass of carbon 12, 13, and this one 14. Now we are having all of these in nature. It would not be correct to say that the mass of carbon is 12 AMU or 13 AMU. Now this one, because you're having in a random sample of carbon all of these. So how would we be able to express the mass of carbon? What we'll have to do is to find the average atomic mass of all of these isotopes to answer that question. So what we'll do is we'll show you how to find the average here. First of all, let's see how this is done using marble as an example. Let's say you have 10 marbles, and 9 of them have a mass of 10 grams each, and 1 has a mass of 12. How do you go about finding the average mass of the marbles? You know that more than I do. So you take 9 of the marbles and you multiply by the mass for each, you get 90 grams. So these 9 marbles will contribute a mass of 90 grams. This one here contributes a mass of 12 grams, so a total mass of 102 grams. So the average mass that we found by taking this mass here and you divide by 10 marbles, so you get 10.2 grams per marble. Same thing we'll have to do now when you want to find the average atomic mass for the isotopes of a particular element. We'll have to know its isotopic abundance or percentage abundance, and which is defined as the percentage of one of the isotopes in a natural sample of a mixture of isotopes of an element. What is shown here next are their percentage isotopic abundance in nature, or relative abundance. Carbon-12 has an abundance of 98.9. So you see, this is the most abundant one, followed by carbon-14, which is 1.10%, and this one is very, very small. So what we'll do, because it's insignificant, we'll not use this in calculating the average atomic mass for the isotopes. So this is what we do, just like we did for marbles. You take the mass of this, which is 12, and you multiply that by its abundance. So carbon-12 will have that mass, you multiply it by its abundance, which is 98.9%. Then you add that to what is the mass for these, which is 13.00 U times that percentage abundance. But because this is not significant, we leave that out of the calculation, and then you divide whatever you get here by 100%. And in the end, you'll end up with your friend here, which is 12.01 U or AMU. Okay, so that is how we find the average atomic mass of one particular element. You can use the same strategy to finding that for all the other elements that have isotopes. So I want to point out something here to you you'll see something like this in the periodic table. And if you didn't understand isotopes and how you find their average atomic masses, you want to know where you're getting these decimals from. Note that these decimals are the result of finding the average atomic mass for all the isotopes of these elements there. And sometimes people might want to say, oh, how are we getting these decimals? They might want to feel that you're using fraction of protons and neutrons. So note that they're not fractions of protons and neutrons. They're just the result of finding the average mass for all the isotopes of these elements there. So what we'll do now, I'm going to use 3 elements to establish the mole concept. The elements that we'll be using are shown in this table. Hydrogen 1, carbon 12, magnesium 24. The atomic mass for hydrogen 1 is 1U, carbon 12 is 12U, magnesium 24 is 24U. Put that into another table. Here you see now, I'm giving you the nuclei of all of these here. That's hydrogen, that's carbon, and that's magnesium here. If I ask you something now, how many times do you think that carbon is as heavy as hydrogen? What would you say? If you say 12, then you're right. The same thing if I ask you now, how many times is an atom of magnesium 24 isotope is as heavy as one atom of hydrogen? If you said 24, then you're right again. So that sets the stage now for our real understanding of the mole concept. But before we go there, some salient points to remember. The mass number given for an atom is used to represent its atomic mass. You did that already. Every isotope has its own atomic mass. Okay? Carbon 12 will have an atomic mass of 12 AMU. Carbon 30 will have an atomic mass of 13 AMU. Carbon 40 will have an atomic mass of 14 AMU. Use these here with the average atomic mass list. This is found when you take all of these here and you find their average. So if you're talking specifically about carbon 12, then we're talking about this atom here. If you're talking about carbon found in nature, then we'll have to use this number here because this is the average mass for all of these guys here. So hope you remember these things, okay? So again, I put this here for you to see again, so you'll understand what is happening here. These are the average for all the isotopes. Now watch this. When calculating the molar mass for any element, note this, any element, the average atomic mass is used. When calculating the molar mass for one of the isotopes of an element, the specific atomic mass of that isotope is used. If I want to know what's the molar mass, say for carbon 14, I'll have to use carbon 14. Okay? But if I want to find the molar mass of carbon that's occurring in nature, we'll have to use 12.01.